Today I want to talk about continuous random variables, how they're different than discrete variables, and how you can convert them sometimes. So let's get started. Continuous probability distributions is the other half of the set, along with discrete distributions, that make up random variables. Continuous random variables differ from the discrete distributions like this. Continuous distributions assume that any value in a given range or interval is allowed as an outcome. So there are an infinite number of possible values within that interval itself. There are an infinite number of weights that an individual can be, because you can carry them out to any number of decimal places in whatever the units are. Anything dealing with time or distance usually can also be thought of as a continuous random variable, like the delivery time of a package. If you force the delivery time to be an integer, like days or hours, some set unit, even though it can go to infinity, it can be thought of as a discrete distribution. But once you allow for seconds and fractions of seconds, then the delivery time for an Amazon package, for instance, is a continuous random variable. Everybody has a variety of electronic devices that they use, and the lifetime or usage time for an electronic component or a device is also a continuous random variable because it's measured in time and fractions of seconds are allowed. Same with calls in between coming into a customer's call center. That also works for customers walking into a retail outlet or some kind of storefront. And also the monthly demand of a product, especially since it's nonlinear and you can use fractions for estimating the number of people willing to purchase a product at a given price. Of course, like 4, if you make that an integer, then you can think of it kind of as a discrete, but in the calculations, it's sometimes more precise to use fractions. Informally, a smooth histogram is a function. So instead of having the nice towers of a discrete distribution like a binomial, then, for example, the continuous random variable graph below shows the different endpoints. A is the minimum for the graph, B is the maximum, and that blue curvy line right there, that nonlinear line, is a smooth histogram for the relative frequencies, normally known as f of x. Now, I don't want you to think of f of x as an actual probability. It's a probability within a very small range around that value of x. Because there are an infinite number of possible values in a continuous random variable, the probability of getting a single one is exactly 0. We have two properties here for the probability density function, or PDF, of a continuous random variable. The first is the integral sign in the calculus, saying that over the entire range, so from negative infinity to positive infinity, that function itself, f of x, is 1. Another way to say that with calculus is that the area underneath that graph, f of x of whatever the random variable is, will sum to 1. And all relative frequencies have to be greater than or equal to 0. 0 is allowed, but there's no such thing as a negative probability. So the probability can be thought of as the area underneath a curve given to endpoints. Given the graph on the right there, we see that x1 is the minimum now, and x2 is the maximum for a given range. And that shaded area that's gray will be the probability. We use calculus to find that out. We make the endpoint x1 and x2, take the frequencies, add up that area underneath the curve, and that is the given probability. So, quick refresher. What's the probability that any given value in a continuous random variable is a constant? I'll answer that in the next one. That answer is 0. Because again, there are an infinite number of possibilities. So the odds of getting 1 is 1 divided by positive infinity, which is 0. The normal distribution is by far the most popular continuous function, and for various statistical reasons, it's incredibly important and used all the time. It's used to describe the continuous random processes or phenomena. And it also can be used as an approximate or a replacement for the discrete probabilities for binomial and Poisson. The normal distribution will be used throughout the rest of the course, of course, to gain some statistical inference. The normal probability density function is listed right here. There's f of x. We have a few very famous values in this PDF. We, of course, have pi down the denominator, and e. They're rough. Since they're irrational numbers, of course, those two numbers go on forever, but the approximate values are listed right below. X is the random variable itself that comes from the distribution, where mean and the standard deviation are the two probability parameters for it. In Excel, to figure out the probability given some value x, we use norm or normal.dist for distribution. And it takes 4 inputs right there. X, the value itself, mu, the mean of the given normal distribution, and sigma, so the variance, the square root of the variance, and then finally 0 if you want just the PDF. Normal distribution is also known as a bell curve. Original term was Gaussian. It's bell-shaped, and it's also symmetric, meaning that there's an equal probability that a value is less than the mean as it is greater than the mean itself. It also means that the mean, the median, and the mode are all equal. And a specific property of the normal distribution is that the middle 50% is within 1.35 divided by 2 standard deviations around the mean. So you divide that by 2 and go greater than the mean and less than the mean, and the area underneath that curve is 50%. An important property of the normal distribution as well is that it has an infinite range. No matter how unrealistic, no matter how improbable, all numbers from negative infinity to positive infinity can come from any normal distribution. Highly, highly unlikely. In some cases, in real-life simulations, we do what's called truncating, where we make sure that it doesn't go below 0 if we're dealing with something natural like production of cars or a number of successes or something like that. Common intervals for a normal distribution is that within 1 standard deviation, 68% of the area falls within 1 standard deviation of the mean. That jumps up to 95% if we increase it to 2 standard deviations. And finally, 99.7 for 3 standard deviations, either above or below the mean. These are very common and known values when describing the normal distribution. A normal distribution only takes 2 parameters. It needs the mean and the standard deviation. But given those different combinations, there are an infinite number of normal distributions themselves. While they have the same properties listed before, they can look fairly distinct and different from one another. As shown on this slide, A, B, and C are all normal distributions, but you certainly would agree that they're not identical. So again, since it's a continuous random variable, the probability given a range is the area underneath that curve. So the probability that x, whatever value that is, falls between the lower bound of C and the upper bound of D can be expressed in calculus to find that area underneath the graph. Since there are an infinite number of normal distributions, it's sometimes important to convert normal distributions to what's called the standard normal. The standard normal distribution has a mean of 0 and a standard deviation and variance of 1, because the square root of 1 is 1. So the standard deviation and the variance are the same. You could take any normal distribution and convert it to the standard normal, which is often referred to as the z distribution, or z. So to convert a normal distribution to the standard normal, you take the value itself, the random variable, and you subtract its mean, and then divide by the standard deviation, and that will convert it from the original normal distribution to the standard normal with a mean of 0 and standard deviation and variance of 1. Given a value x for a standard normal distribution, we talk about the z-score. And the sign is important because any positive number means that's greater than the mean, and any negative number represents that the value is below the mean. A standard normal distribution has all the same properties as a normal distribution, just centered at 0 with a predetermined deviation or standard deviation and variance of 1. Let's look at this example right here. The graph on the left is a normal distribution. That's what the large N signifies. It means it's distributed normally. The first parameter listed is always the mean. So this normal distribution has a mean of 5, and it has a variance of 10 squared. This is common notation for normal distributions because the variance will be 100, but can be calculated from that, and the standard deviation, therefore, is 10. So what if we want to determine what the probability that a value sampled from this distribution is between 5 and 17.5? There are ways to calculate that directly, but if we want to standardize this distribution, we shrink that normal distribution that has the mean of 5 and standard deviation of 10 to the graph that, in the lower right or on the right side of the graph that now is centered at 0 and has a standard deviation and variance of 1. The probability underneath the graphs are exactly the same. So the shaded area on the graph to the left equals the shaded area on the graph to the right. And that's a key feature. You don't lose anything by standardizing a normal distribution. So first we can standardize this distribution. So it starts off with P, the probability that x is between 5 and 17.5, is the probability that we get to a z-score that is between 0 and 1.25, or 1.25 standard deviations greater than the mean itself. This probability can be broken up into the probability that z is less than or equal to 1.25 and the probability that z is less than or equal to 0. There are predetermined tables called a normal table or a z-table that has these values printed out. But since we live in the digital age, most of the time we can skip that part and just calculate it in Excel or Minitab or some other application. But I will say from right here that the probability that z is less than or equal to 0 is 0.5 or 50% because it's right, the mean and the median and the mode are all the same. And for the standard normal, that's 0. Here's a standard normal probability table. This is the positive side. So the first digit is the z, that's listed as the row. And then the second digit, or the 100th place for the z-score, is up at the top. We find the intersection of the two. I've highlighted the two we need right now. We needed a z-score of 0, which is conveniently right there. It's the intersection of 0 and 0, row and column. And then we need 1.25, which is the intersection of the row 1.2 and the column of 0.05. Sure enough, the z-score of 0 is 0.5, and the z-score of 1.25 is 0.8944, or 89.44%. The difference of those two numbers will give us the shaded area, and therefore the frequency between 5 and 17.5 in the original normal distribution. Here's the property, the commutative standard normal property right here, where if you have two endpoints, A and B, you can split that probability into two calculations. And with the standard normal, you can just look up the tables, or in Excel, have it in two different cells. So the standard normal right there is between 0 and z at 1.25. Speaking of Excel, here are some common functions that will help us. Excel keeps the format of the distribution first, and then .dist if we want the distribution. And then on the next slide, we'll show .inv for the inverse. We'll get to that. When we deal with the standard normal, Excel adds the .s in between the norm and the dist. So if we want to compute the probability given a z-value, so a standard normal value, then we use the norm.s for standard, .dist for the distribution. And it looks like that. Probability of z, that z-score, is less than or equal to some number is norm.s, .dist, and then that value. It only takes the one parameter, and that's the z-score. For a normal distribution that we have not standardized, we use the norm.dist function in Excel. It will give us the cumulative probability for x, but then since it's a non-standard normal distribution, we have to provide those parameters. So mu for the mean and sigma for the standard deviation. So usually requires standard deviation and not variance for its different probability calculations and functions. So if we have not standardized the normal distribution, we say norm.dist, the particular x value, whatever that happens to be from that normal distribution, and then provide mu, the mean, sigma, the standard deviation, and the last parameter is a 1 to add up all the values. So that's where cumulative probability comes into play. That's the less than or equal to part instead of just right around that x value itself. So going back to our previous problem, we used the table to find the two values and subtracted them from each other, but we can do the calculations in Excel. So once we've standardized it, we use norm.s.dist. Two calculations, one for 1.25, the other for 0, and there are our numbers again, 0.8944 and 0.5. We get down to 39.44%. Here's proof that you don't lose any value by converting from a normal distribution to a standard normal, because the norm.dist function can be used right there. We give it 17.5, that was the larger number. We then provide the second number, which is the mean 5, then the standard deviation 10, and we don't forget the 1 for the less than or equal to part, cumulative. Do the same thing, but for the lower bound, for a value of 5, get 0.8944 and 0.5 again, equals the same probability, 39.44%. So we're saying exactly the same thing. What's the probability between 5 and 17.5 given this normal distribution, this specific one? But we can always get it down to the standard normal and say, what's the probability between 0 and 1.25? Say they are equivalent and mean the exact same thing. What if we start with the probability and we want to find where that x value is? So what's the probability for a z-score that will give us 0.75 area shaded underneath the curve? Well, two ways to do this. If we have a standard normal table here, which is easily searchable online and then comes in every textbook ever made for statistics, we can look that up. So we, instead of start with the z-score and find the probability listed at the intersection of the row and the column, we know the 0.75, so we know the probability already, and look inside the table and then find the row and the column. So 0.75 is somewhere in between the two numbers I've listed right there, probably a little bit closer to 0.67 as opposed to 0.68, so we know it lies somewhere in between. That's the best we can do with these predetermined tables. Excel is the, I think, more intuitive and faster way to find these numbers. We use now the inverse. Same rules apply. We have a normal distribution, so we're using norm. We've standardized it, the normal distribution, so we use .s. This time, we provide the probability p in order to have Excel calculate what z-value would generate that probability. The .dist, or distribution function, is the opposite. But that's kind of the normal one, or the regular one, rather. So this is referred to as the inverse function of that, so .inv. Again, we only put in the one parameter, norm.s.inverse, or inv, put in 0.75. Sure enough, it kicks out what that z-value was that we found in the table but didn't have that thousandths decimal place for, but turns out to be 0.674. Again, if you don't standardize a normal distribution, you can use the non-S or the norm.inverse function, and that'll do the same thing. But since it's non-standard, you have to provide the mean, mu, and the standard deviation, sigma. As I said, the normal approximation of a binomial probability is one of the main features of the normal distribution. Recall that a binomial distribution is discrete, that you have a certain number of trials n, and a probability, however you define it, of successes, but that probability is constant and represents the probability of that trial being a success. Well, 1 minus p is the probability of that trial being a failure. In order to be justified, to be on solid statistical foundation, we have to do a fast little check. We need to make sure that n, the number of trials, is greater than 20. We need a large enough sample size. It's not too bad. We also need to make sure that p isn't too small. So n times p, that product needs to be greater than or equal to 5. So that's the number of trials times the probability of success. And then we also need to do that with n and the probability of failure, or 1 minus p. Make sure that's above 5. So for very small probabilities, then we would need a larger sample size. But if p is reasonable, then it doesn't take that many trials above 20 to make this work. The expectation of a binomial distribution is n times p. So that becomes our mean for the normal approximation of the binomial. And the standard deviation of the normal approximation is n times p times 1 minus p. And we take the square root of that. The final little piece is sometimes tricky. We need to add what's known as a continuity correction factor, sometimes CCF. We need to add or subtract just a little bit because the continuous distribution is used to approximate the discrete. So if we have, for example, in a binomial distribution, we could tell you exactly what the probability that x is 10 is, but since we are changing from a discrete to a continuous, we need to increase the sides a little bit. We need to correct for this, this break that's no longer there in the discrete. So it is smooth now. So we change x equals 10 in the binomial to probability that x is greater than 9.5 but less than 10.5. So we add just a little bit there. It's called a continuity correction factor. Let's do a fast example. Let's assume we have a binomial distribution with 100 trials and a probability of 0.4. And I want to find the probability that we are successful between 30 and 50 times. Using the binomial distribution, we find the result is nearly 97%, but it takes a very long time to calculate all of those separate different probabilities and add them together. We check n times p, that's greater than 5. N times failure, 1 minus p, is greater than 5. And 100 certainly is greater than 20. So we're on solid ground there for the 3 different approximation checks or requirements. So for the normal approximation, we use the continuity correction factor just a little bit, move that 30 for the endpoint on the binomial down to 29.5. We up the 50 on the binomial to 50.5, correct just a little bit. And notice how close we are for that normal approximation. It's difficult to do that individually for the binomial since it is discrete. You have to do it over and over and over again. But for a normal, we can do it quickly in any software application or with pen and paper and then look it up in the predetermined table. We don't lose very much precision at all using the normal approximation as long as we have those 3 little checks. So in conclusion, many variables in real life are continuous. Time is important, distance is important. We like to track those values when talking about different records or different items in a study or people's responses to any number of questions or their behavior. So with this video, we've concluded the 2 main types of random variables. The discrete, which can be infinite, but certainly some type of limited number with known probabilities. And then we have the much more common normal distribution that is important because it can even be used to approximate a discrete distribution. So until next time, thank you.